Hello everyone, I am Sofia Bucarelli from Sapienza University of Roma. In this video, we'll present our recent work, a topological description of loss surface based on Betti number. In recent year, the investigation of the theoretical foundation of machine learning and deep learning models has gained increasing attention as the research community has decided to delve deeper into the reason why these models can achieve exceptional performance in different application fields. From the theoretical point of view, the characterization of the loss function to be minimized is crucial as the training efficiency relies on the shape of the loss function. And several works have already dealt with the analysis of the surface of the loss function, and our work fits into this line of research. More precisely, this is the characterization we gave. So given a layer neural network n, we denoted by n, and an empirical loss function computed on some training data L of n, we will measure the complexity of the empirical loss function L of n by analyzing the topological complexity of the sublevel set S of n. That is the set defined where E or theta are the parameter of the network, so the set defined as the parameters, so that the empirical loss on n is smaller than a constant c. Such an approach is natural since the set S of n observed at each level c provides the form of the shape of the loss function. For instance, if the loss has k isolated minima, then for some small constant c, S of n will have k disconnected components regions. In this paper, the topological complexity of the set S of n is measured by the sum of the Betti number of this set. The upper bound is derived, so the upper bound for the sum of Betti number is derived for feed-forward neural networks with different number of regions and different number of neurons per layer, and varying the number of training samples. We consider as loss functions binary cross entropy and mean-square error, and moreover, as activation function, we assume that the nectar has a Pfaffian activation function. The class of Pfaffian function is broad and includes most of the differentiable functions that are used as activation, such as hyperbolic tangent or sigmoid. And so, more precisely, our contribution can be summarized as below. We derive we derive a theorem that states that if the activation function is Pfaffian, then the empirical loss function is also Pfaffian, and for Pfaffian function we have what is called a format, so a sort of complexity of this Pfaffian function, and we derive this format for mean-square error and binary cross entropy empirical loss, and from this we were also able to provide an upper bound of the sum of Betti numbers for this empirical loss function, and table 1 summarized the results. Basically, these bounds were obtained as a function of the number of layers, the number of neurons per layer, the size of the training set, and and we can see that the complexity changes. There is a qualitative difference of the complexity of the loss function for shallow, so shallow networks, so networks with only one hidden layer, and deep network. In general, the complexity increases super exponentially with the number of layers or neuron per layer, and exponentially with the number of training samples. Moreover, we also have some results showing that adding L2 regularization term and skip connection does not affect our analysis, so the upper bounds stay unchanged. Thank you for your attention.